Hello and welcome to When Anti-Patterns Become Best Practices. In this session, we're going to talk about a number of features that have been introduced in recent releases of SQL Server and Azure SQL Database that have taken formerly anti-patterns, things like using scalar valued functions or multi-statement table valued functions, and made them into not necessarily best practices, but things you can do and have your code perform efficiently without making any changes. I'm Joey D'Antoni. I'm Principal Consultant at Denny Cherry & Associates Consulting, and I'm going to lead you through this session. Hello and welcome to our MySQL Bit session. This is, as I mentioned in the intro, when anti-patterns become best practices. I'm Joey D'Antoni. I'm Principal Consultant at Denny Cherry & Associates Consulting. Microsoft has honored me with the Most Valuable Professional Award 6 times. I'm also a VMware vExpert. I've worked with SQL Server for over 20 years. You can find me on Twitter at jdanton. You can also find my blog at joeydantoni.com. I'm also on LinkedIn and Twitter, and my email is joey@dcac.com. I'll give you all that information at the end of the session. So here, what we're going to cover today is understanding some anti-patterns in T-SQL. There are a number of things that throughout time we've always come to recognize as anti-patterns, and some of those things will probably remain anti-patterns forever. But we're also going to talk about other subjects like scalar functions and table-valued variables, or table-valued functions rather, that were formerly anti-patterns but now work. I'm not going to say they're best practices per se, but they work really well in SQL Server 2019 in a lot of instances. We'll talk about how those things change and what improves, and we'll also talk about why Microsoft made these changes. They have a better understanding of the way the database engine works nowadays, and I think that's because managing Azure gives them a better perspective. In addition, they have telemetry. We'll do some demos, of course. We'll walk through these features in SQL 2019 and show you how performance improves between 2017 and 2019. In some cases it's similar, in some cases it's different. We'll also talk about things that are still bad. There are still practices that are never going to be really good, whether it be SQL Server or any other database engine. Which leads me to my first anti-practice. This is probably the worst anti-practice there is in all of databases, and this is doing row-by-row based operations. In this bit of code, we're doing a loop here, but you may also see a similar effect with a cursor. So on line 15 there, we're declaring our loop variable as an integer. We're setting the value of that value by being select the minimum key value from the table, and while that variable is not null. And then we might do some stuff with the current value of loop var that might be update a value, and then we go get the next value from the table. This is really bad for a number of reasons, and I'll start with we could potentially do this all in one large set-based operation, which is what databases are really efficient at. Well, application code like C# is really good at dealing with small sets and iterating through them. Doing this on a database where we might have a really large table is not a good thing. Granted that select minimum key value could be kind of expensive, especially that second query where the variable's less than the key. We might have to scan a whole column to do that, and if the indexing is not good, we might have to scan a whole table. But moreover, doing this is just very expensive and not a very efficient way to do things. This is one of those things that will probably always be a database anti-pattern. There's no way to kind of retrofit the database engine to handle this code better. It's just really, really inefficient. So what do you do to replace these? You do set-based operations wherever you can. You use temp tables if you have to. You do whatever you can to make everything one operation and one transaction. That's how we make code more efficient. So this is another example of a problematic pattern. And I think the way I can describe this best is that views inherently aren't bad. If we think about what a view is, a standard view, not an index view, a view is just a way to save a query effectively. They're frequently used, I find, where I come across these the most is in BI systems, where they're used for kind of development purposes, right? The team will build a query. Maybe it's a query that supports a report, and that view will get used. Hitting that view is easier than having to teach business users how to join a bunch of tables. They can simply select all the data from the views. The problem comes in, as you see here, starting on line 16, where we start to reference, or actually it's line 25, where we start to reference other views with our view. This gets really confusing to the query optimizer because these are what are known as nested views. And the worst story I have about nested views is that I was once working on a system in a large company, and they had nested views that were 8 levels deep. The database optimizer can't generate stats on anything like that, so it simply starts scanning everything. It's really, really, really problematic in terms of performance, and it's really difficult to troubleshoot because you have to effectively unnest the views and then try to performance tune each of those individual queries that make up the view in order to get to a resolution. It can also be confusing in terms of data quality. So a single layer, maybe even a double layer of nested views is fine, but you don't want to go anything beyond that. It becomes a really, really hard problem to unweave. Your execution plans aren't necessarily going to make any sense. They're going to be extremely complicated. The optimizer may even time out because it may not be able to generate a plan in time in order to fulfill your query. So this is a really bad anti-pattern as well, and it's something that I think is just you want to avoid. And like I say, the kind of warning signs of it are that you have a layer of views that become popular with a set of users who maybe do some light SQL development, whether they be business analysts or developers who don't have a whole lot of experience with SQL. And then they start referencing each other. And this is where you can get really problematic behavior. And the other bit of that warning I'll give you, it's pretty easy to get into a situation where you have a lot of nested views. Once you begin using those in your code, it can be really problematic to be able to untangle them. So it's really important to try to avoid this situation where possible and just enforce it through code review and things like that. Here's another scenario where SQL Server performs poorly, and just about any other database engine does. Here, we're doing a couple of things wrong. So the first is that we have a function in our where clause. So we're saying, give us the leftmost value of address line A, the first 4 characters. We also have what I would call a data modeling here problem, because we're looking for an address number, perhaps on a street or something, or maybe all the instances of the address 4444. And we don't have a street number value in our column, but having this function in our where clause is going to cause SQL Server to have to scan the entire column. That's not going to be very efficient. Even if we have an index, it's still got to read all those records. We might also even have to read the whole table if we don't have that column indexed properly. So this is a very expensive pattern. This isn't something that you can really fix. We can't have function-based indexes. So really you have to address this in your data model and by using proper data types. There are some other ways you can avoid scan. So you could also say where like 4444 wildcard with just the trailing wildcard. Likes with leading and trailing wildcards will scan. But and this comes down to a feature of SQL Server called search arguability, or sargeability, as it's more commonly known. Columns that are sargeable can be seeked, and that means we only have to retrieve the page that would have this value. Whereas if a search argument, which is our where clause here, is not search arguable or sargeable, we would have to scan the column. And as we know, generally speaking, when we're looking for a single value, a seek is always better than a scan. Table valued functions seem like really wonderful operations to developers. They're really easy to code. They return data kind of in the way an application developer would expect, that it comes in both a set of data. So we see that moving across. So that's kind of a really nice benefit of this function, this table valued function element. You can use these to exchange data between objects in your code. You can use them to exchange data between objects in your stored procedures if you have to. So SQL Server doesn't have an array data type. So I've used this when migrating an Oracle system. that had array inputs. The problem here is that this traditionally hasn't worked real well in SQL Server. And the reason is table valued functions have a row estimate of 1, and multi-statement table valued functions have a row estimate of 100, starting with SQL Server 2014. That works great if you have a very small number of rows. If you have a very large number of rows, that can be very problematic in terms of your performance and your downstream execution plan. If SQL Server is anticipating that it's only going to have 100 rows to join, you're not going to get a lot of memory granted to your query, which means if you have 2 million rows that you're joining, that entire join is going to spill out to TempDB. And what we mean when spill out to TempDB is SQL Server is going to have to write a whole bunch of records to TempDB. Depending on the speed of your disk, that could be not too impactful, but generally speaking, large TempDB spills are very bad for your overall system performance, so it's not something you want to do. You also might have the database engine make suboptimal downstream join choices. A nested loop join over thousands and thousands of rows is going to be very expensive, whereas if SQL Server knew it had a large number of rows, it might have done a hash join. So the big problem with these, and we'll talk about this in a second, is these were blind to the database optimizer. So the database optimizer couldn't see what was going on, and you'll see it in my demo, and made poor decisions. And this was a place that this isn't really something that should inherently be a bad practice, but it is because of the way SQL Server interprets these objects. So there's nothing inherently wrong the way row by row operations are, or using functions in your where clause, but this is kind of bad because of the way SQL Server behaves. And we'll talk about how this gets fixed in a little while. So this is a user-defined scalar function. This is a particularly terrible one. I found it on a .NET code instruction site. We're doing a calculate age on the fly. And the reason why developers like to use these functions is they can be referenced in a query. So we can do a calculate age within our query results and get that. Couple of problems with that. Traditionally, scalar functions have been executed on a row by row basis within your query. They inhibited parallelism in your query. So if you had a scalar function referenced in your query, there was nothing that you could do in order to generate that kind of parallelism or improve performance. They were also really blind in query plans. If you're running a scalar defined function, you couldn't really see what was going on in terms of performance in the plan. You just kind of saw a black box, and that was also pretty problematic in terms of what was going on in those queries. This is something that, once again, kind of unlike, I'll make an exception for this scalar function because it's kind of universally terrible. But in most cases, the use of scalar functions is not inherently bad programming. It's because of the way SQL Server treats them and operates on them that this is an anti-pattern. It's not something that I would say per se is a total anti-pattern. So we'll talk and see how this is improved in SQL Server 2019. Just want to say, no databases were harmed in this collection of anti-patterns. I found some of these on the internet in various places. This is not actual code I took or masked from production. I've seen a lot of bad stuff, and the nested view thing really happened. That happened poorly at a client. But it's important to note that I didn't do anything too bad to hurt anything here. So why are these anti-patterns? We've talked through this a little, but in the case of those cursors or loops, they just don't take advantage of things databases do well. It's kind of bringing an application development mindset into a database engine. And that's a fairly common thing, because I think, as we all know, application developers don't tend to think of databases first, or really a lot of them don't necessarily understand the benefits that they can be getting from a relational database. And so that's a place where you need to coach your developers to understand the things databases do well, which are set-based operations. In terms of every other anti-pattern that we've highlighted here. The big difference is that they cause the query optimizer to be blind to the number of rows it's processing. The query optimizer is a really, really complex piece of software, right? Building database engines is hard. There's a bunch of smart people in Redmond and all over the world that work on SQL Server in order to make it optimal. And the only way you get optimal plans is for SQL Server to know the number of rows it needs to retrieve every time. All of these anti-patterns, they pretty much don't, like the nested views, SQL Server can only read so many statistics, cursors and table valued functions. Those are things that SQL Server just doesn't know how many rows, so it takes a fixed guess, at least prior to SQL 2017. When the query optimizer doesn't know what to do, it scans, because that always works. The other problem, the query optimizer, remember, you allocate a certain amount of memory for the join operations in any given query. If you don't have enough memory, that spills to disk, and disk is slow. Additionally, scanning all the time is bad, right? We're going to add I/O contention to our system. So having the best statistics and the best information available to the query plan at all points is really critical in terms of how your queries are going to perform. So if anything Microsoft can do to get SQL Server better information about the queries it's running will result in overall better performance and throughput, because things will run in a more efficient manner. So what changed at Microsoft to fix these issues? And I think the big thing, and I had a discussion with an engineer last week about this, is that very much Microsoft was really good at building database engines, and they did it for 20 plus years of SQL Server. SQL Server just had its 25th anniversary a couple of years ago. What they weren't necessarily good at is understanding the way SQL Server operated. What changed, and you can see from this slide, is Azure, the cloud. When Microsoft started having to manage SQL Server at scale, which they do via SQL Azure, they did a couple of things. They wanted to capture information so they could operate and improve things. So that led us to a feature we all know and love called the Query Store, which came in SQL Server 2016. It was in Azure SQL Database a little bit earlier. And that gives them what we call a telemetry pipeline. And beyond that, there's other telemetry components. I'm not going to just say that the query store is their only telemetry, but this lets them see queries, and the telemetry pipeline is fully GDPR compatible. They've been very careful with anonymizing data, but you get to see millions of databases and millions of queries, and you get to identify the queries that perform poorly. That lets them focus in on these anti-patterns, things that developers are doing that perform poorly, and focus their investments in SQL Server into those areas of databases. So that's kind of a really critical thing to me, that they're able to see what's breaking for customers, validate it with folks like us that are MVPs, and then focus their investments in those areas. Like if one person's having one performance problem, it's probably not worth making a big investment. But if you see the same problem happening over and over again across multiple customers, it lets you investigate and have a better understanding of how your users are using your product. In turn, we got a bunch of new features. And this is something that has come into SQL Server in the last couple of releases, really starting with probably 17 and adding some in 19. And these are features called intelligent query processing. Intelligent query processing is a family of features. The couple things we're going to be focused on today is table variable deferred compilation, as well as interleaved scalar UDF inlining. But we have a number of query features that offer improvements. So we have scalar UDF inlining that's going to change the way your scalar functions get executed within the database engine. This is going to be a really cool demo, because you're going to see kind of night and day performance, plus you'll get better information. We also have a proximate count distinct. That's a feature that lets you do count distinct where you're not 100% sure about or care about the accuracy of the value. Where you might want to use this would be in pagination is a common use case. We have batch mode for row store that kicks in for some analytic queries. Okay, say the big one here is table variable deferred compilation. I'll walk you through this and how it works in a second when we do this demo. But we also have memory grant feedback. So if a query is paging too much because maybe a poor variable choice or parameter sniffing or something like that, we can get memory grant feedback based on the last execution of the query. So if it spilled the tempdb, we can get information back, or we can get more memory. If it had way too big of a grant, which could impact concurrency, causing resource semaphore waits, it can give it less memory. And we also have adaptive joins in batch mode. One of the kind of interesting things about these features is they are all tied to compatibility mode. So the features we're mainly going to talk about today, table variable deferred compilation and scalar UDF inlining, are SQL Server 2019 or compatibility level 150. Some of the other features, interleave execution, which is multi-statement table valued functions, those are 140 or SQL Server 2017. So we'll walk through all these. It's important to understand Microsoft's support model, though. They're trying to support SQL Server by compatibility level, and this is more for your vendor applications. So if you have a vendor that says, we only support SQL Server 2017, and you want to run in 2019, Microsoft's support model is that you can run on 2019, but stay in SQL Server 2017 compatibility mode forever, and they'll support you all the way through. This offers us a number of benefits in terms of where we are and how we're doing with SQL Server and how we have downstream support. Next, we'll do a demo on scalar functions and table variables. The first demo we're going to do is looking at multi-statement table valued functions. And here we're creating a pretty big function based on potential for outlier events. So we're looking at recessions, hurricanes in various parts of the United States. So we're looking at South Atlantic, East and South Central, and West South Central based on these parameters. So those are our effective parameters that we can pass in. So the type of event and the begin and end order date key, as we see in the first line of our function. You can see we're inserting into a table variable the outputs of a select statement. And the only difference between these is in the case statements. So you can see the case statements is going to change the when and then quantity. And based on those values, we're also going to determine which states are involved. If it's a hurricane event, different states are going to be involved. So we're going to have a different set of values each time we go to execute this. And if we scroll down to the very bottom of this function, it's a pretty long function. We'll see the last one here where we're changing the values for East South Central and then West South Central. This is a fairly complex multi-statement table valued function, but by far not the worst that I've seen. And then we see the return, end, and go. And I'm going to trip over executing this for a second. So we'll go ahead and execute this to create this function. I think it's going to take me 2 times to do this. The joy of recorded demos. So here I screwed up there. So we'll just go ahead and re-highlight that and execute it. Went a little bit too far there. Here we go, and we'll get this executed now. So now that's created. We'll go ahead and go run this in compatibility mode 130. So this is we're gonna ensure that we're not running on the newer compatibility mode. So this is having us run in SQL Server 2016 compatibility mode. So our standard expected behavior in 2016 is that we're gonna see this have an estimate of 100, a fixed estimate of 100 rows. But let's go ahead and execute that so we can see. So we're joining on our values on mild recession with 1/3/2013, 1/1/2013 and 10/15/2014 as our input parameters. So we'll go ahead and run this query. And we see this is going to take a few seconds to start returning rows. The performance of this is not good, but it's not atrocious. It took about 4 seconds to run. I'll zoom in here. We can see that we have a couple of those warning arrows on our operators, which are our hash matches or inner joins. That means SQL Server is spilling to TempDB. Here we see that this operator wrote 772 pages and then read them from TempDB. And we see this guy wrote and read 1,950 pages. That's a decent amount of data. That's, 8 meg. If we look at this estimate, we see that we estimated that we were going to have 100 rows to be read, and we actually had 231,000. What that's going to cause is those spills, because SQL Server is not anticipating that it's going to have enough memory in order to do that. So it's not going to allocate enough memory to this query, which means we're going to write to TempDB, and that's always going to be fairly expensive in terms of the operation. So that has a number of downstream effects, including probably potentially even picking less efficient join choices than we might otherwise have. So getting that number right is very important, and we'll observe the difference in performance when we change compatibility mode here in a second. We'll zoom out here in a second. Now I'll change the compatibility level to 140 or SQL Server 2017. This is one of the features that was introduced in 2017. This is not 2019 specific. So if you're not on the latest release and you have this, you can take advantage of this feature. You'll note though that in 2017, for this particular feature, you have to be in batch mode. So that implies that there's a column store index somewhere in the plan. So we're going to go ahead and run the same query with the same input parameters. Except I'm going to connect to the right database this time because I was in master. And now we see, as opposed to the 4 seconds, we ran in just over probably a second, 2 seconds. So almost 50% improvement in runtime. And now if we hone into our execution plan, we don't see any spills. We see a nice hash match. The plan's not that dissimilar to what we saw, but the row counts are accurate. So we see the estimated number of rows for our table scan is 231,412. And that means all of our downstream input operations are going to know how many rows are in that operation. So here we don't see a spill, we see a good join. That means we're gonna be happy in terms of that join input for how much memory we have. This means we're going to have more efficiency in our queries. They're not going to run poorly. We see our final join here. There's no spill there either. And then we see our table valued function that we're calling, and we see the estimated rows per execution there. It's 231, so we have the right numbers. So this is a much better scenario for what we're looking for in terms of execution plan analysis. So in the next demo, we're going to look at table variables. So this is all SQL Server 2019 functionality as opposed to 2017. So here we have a stored procedure called customer profits. We're declaring a table variable called ilines, and this is simply going to be all the invoice lines. And then we're going to have our total profit per customer. So we're going to get their iline profit as total profit, and it's going to be a procedure that calls a table variable. So common use case for table variables is being passing data between procedures. So we'll go ahead and create this stored procedure in wide world importers. And now we'll go ahead and warn the cache. So we'll load a bunch of data in from the table so that we're making a fair comparison in query performance. This is just so that the second time we run it, it's not significantly faster than the first time, because that can happen with memory situations. So we're going to run this 25 times, and so you can get a rough idea of what it looks like in terms of perf, because it runs pretty quickly. It's not a ton of data. And since I've recorded this in advance, I can tell you the first time I forgot to turn on execution plan. So we're going to run this twice. But the first time we're going to run it 25 times just to see the performance of it. And you can see it takes a couple of seconds to run each time. It's not very fast. And you'll note I'm not capturing execution plans here. When I run the next query in compat 150, I will be capturing execution plans. So even with the overhead of capturing the execution plan, that's noticeably faster. So this is going to take about 15 seconds total to run. And we're almost done, and then I'll rerun to get the execution plan. Actually, I was a little bit off there. I think it might be over 20. If your time doesn't match your watch, it's okay. This clock is a little slowed down because I'm made things match up with audio and video here. We'll just run this once to get the execution plan so we can see what's going on there. Once I get into the right spot to do that. There we go, and we'll execute this once and we'll see the runtime. So here we can see the runtime. It actually ran sub-second there. But if we look and we zoom in on our select, we see we have a sort spill. So we see that yellow arrow. We wrote 755 pages to TempDB. So we wrote a meg effectively of data to TempDB. And if we look at our clustered index scan for our table valued function, or table variable rather, we see that we only read one row. Or estimated that one row was read, even though we had 228,000 rows. That means we didn't get enough memory, and that's why we spilled to TempDB. So that makes this query far less efficient than it otherwise would be. So these are kind of important things to note. We see we did a nested loops join, which if we had that many rows, might not be that efficient. So hash joins have a higher overhead to do, but they're more efficient for a large number of rows. So that could be a problem here. So we'll go ahead and change compat to 150. And that's done. And now we'll go ahead, and I have execution plans turned on now, so we don't have to worry about redoing that. And we'll go ahead and run this query again 25 times. And remember, that took about 20 seconds on the clock here. And we'll kick this off right now. So you can already see the results are coming back a little bit faster than in the previous execution. What's interesting is how changing that row estimate for this table variable has lots of downstream impacts on our execution plan, and we'll see that here in a second. The plan's actually quite different than what you saw in 130. compat mode. So that took about 15 seconds, or about a 25% improvement. But when we look at the plan, the most important thing we see is no yellow warnings, so nothing spilled to tempDB. We see we did a clustered index scan of our table variable, but we then did a hash join instead of a nested loop join, and that's because the optimizer knew how many rows we had, and it was more efficient. We also see that downstream join is also an adaptive join, which is another new feature to SQL Server 2017 that's dependent on batch mode, that adaptive join. And since we're in 2019, we're also getting batch mode on a row store here. So this is another kind of interesting feature, and it's because of the nature of our query and the aggregation. So that's going to give us some additional improved performance. So kind of 3 of these intelligent query processing features are coming together to deliver us really nice performance here. In here we see we have our hash match, so that behavior changed. Our join didn't spill to tempDB because we had the right number of rows, and SQL Server knew how many rows it was going to have downstream. This adaptive join is based on the number of rows input. SQL Server will decide which join to use, whether to use a hash join or a nested loops join, downstream once it has the actual row count. So this is something that's quite beneficial to lots of workloads, but this is something that was also introduced in SQL Server 2017 as part of intelligent query processing. So the nice thing about this is it makes everything a lot better. The one downside is if you run this query frequently and the number of values in your table variable changes frequently by a large amount, it's going to cache this execution plan with this value. So in this case, we have 281,000. If the next time you run it, you had 10 rows, it's going to think you had 281,000. So if you have that scenario and you don't run the query that frequently, recompile may be a good option for that, just so you're getting the accurate row count every time. And we're just setting compat level back to 130. Finally, we're going to talk about scalar functions. And this is, to me, this is one of the more dramatic of the features in SQL Server. So here we have a query that I wrote just to test, to build out our scalar function. And I'm going to go ahead and execute it and just set statistics, IO, and time on here. And we'll make sure we're using the right database. So this query will take a couple of seconds to run. We can ignore that. It was kind of leftover code that I just ran. Now we're going to create and alter this function quantity. And all we're doing is setting function equal to the sum of quantity from a table. I kind of just wrote this function to prove the feature. It's not really doing anything from a business perspective. I'm not that imaginative. So we'll go ahead and create the function first in wide world importers. And then we're going to set our database. I think we're in 130 already, but I'll reset it here just to ensure, and we'll use the function in our code. We'll get an actual execution plan here as well, so we can see what SQL Server thinks it's doing. So this will take a few seconds to run. This isn't the most dramatic scalar valued function I've seen in this plan. I've had them go from like 15 seconds to sub-second with this feature. I've also had them go from like not even completing to running in a reasonable amount of time. So the first thing that's kind of weird about this is we do get a missing index included in this query, but we see nothing in the queries parallel, so it's all single threaded. And we just don't have a whole lot of operations. We have a clustered index scan, 2 clustered index scans actually. So we don't have a good idea of what's really going on in this query because the scalar function masks a lot of operations. It acts like a black box and it's processed row by row within SQL Server. We'll also look at the time of the query and we see that it took about, I think, 6 seconds here. I'm slow to get it, 5 seconds to return 5,000 rows. This, like I said, this isn't the worst offending scalar valued function or scalar function I've seen, but it's not great either. So what we're going to do here is switch to compat 150, where we can take advantage of scalar function inlining. You'll see a pretty dramatic difference in the execution plan. And I think the most important thing about this feature isn't just the added performance you're going to get out of it. It's the fact that you're actually going to see what's going on in the execution plan itself. That's a big deal compared to servers of the past. So here we see we have a couple of index scans and key lookups. That gives us much more information. That can tell us that we really do need to index a specific column. We see all these additional operations that take place that we didn't otherwise see because they were hidden before inlining of the scalar function. So to me, that's where the real value in this feature is, and the performance is secondary. I love the fact that the performance is better. You can also note that you'll see parallelism throughout the query. So that's another place where we're going to gain performance. Big difference here between 2017 and 2019, or compat levels 140 versus 150 as they are so defined in SQL Server. So this is probably one of the more developer-friendly features. As you'll learn about in the next slide, this feature does have a number of limitations. We see the query ran in a second. So you want to understand your code and understand if it works within this feature. So everything is not magic about these two new features, unfortunately. And this image is from Docs. Scalar function inlining has a number of restrictions. As you can see, you have to write your function in a certain fashion. There are limited options, so natively compiled. You're not using it in a computed column, not a partition function, no CTEs. So there are a number of things that aren't fully supported. You can't do a select with order by without a top one clause. And these will just, if your functions are like this, they'll still work, they just won't inline. So you'll see the same performance you saw on versions of SQL Server prior to SQL Server 2019. Table variables and multi-statement table valued functions get a row count at their first compile time. And what this means is that if your row count is highly variable, you may still get a bad estimate for downstream plans. So just know that if you have a highly variable expected row count in your table variable, maybe either don't use it or recompile if your query doesn't run that frequently. It's always important to understand the evolution of your database platform and adjust your code and designs accordingly. Both SQL Server and Azure SQL Database in compatibility level 150 introduce some features that can really help your application perform better. And you need to understand the limits of these features because they're not perfect and see if your code benefits from them. My contact info, and thank you for attending this session, is at jdanton on Twitter. My email is joey@dcac.com, and you can find my blog at joeydantoni.com.